The state that corresponds most closely to our classical idea of an oscillating electromagnetic field in some mode is what we call the coherent state. And we had introduced this previously as an example when we were talking about the harmonic oscillator. And using our current notation, we'll rewrite this slightly, but it's still the same state. So we'll have our coherent state here for our mode lambda. We'll call it a capital psi. And we've got another parameter in it called n bar, which will turn out to be the average number of photons in the mode, incidentally. So this coherent state here is a sum over different numbers of photons in the mode, so a sum over these different n lambda states here with a set of coefficients, and we'll go all the way from having no photons in the mode to having an arbitrarily large number. And these coefficients are given by this specific formula here. You'll note, of course, they refer to the mode lambda. This parameter n bar is in them, and this is the coefficient for state n corresponding to n lambda photons per mode. These expansion coefficients here have this quantity n bar. As I said, that turns out to be the expected value of the number of photons in the mode. And as before, we note that if we take the modulus squared of these coefficients, we get this expression here, which you may recognize as the Poisson distribution from statistics, with a mean n bar and a standard deviation that is the square root of n bar. Note that in the coherent state, the number of photons in the mode is not uniquely determined. The coefficients here are giving us the probability that we will find a specific number n lambda photons in the mode when we measure the mode. This number is now found to be distributed in this particular state, the coherent state, according to a Poisson statistical distribution. It is in fact the case that the statistics of the number of photons in an oscillating, what we might think of as a classical electromagnetic field, is indeed a set of statistics that are Poissonian. For example, if we put a photodetector in a laser beam, we will indeed measure a Poissonian distribution of the arrival rates of the photons. And this effect is known as shot noise. Note that the coherent state is not an eigenstate of any operator representing a physically observable quantity. It is just an interesting and useful state we can write down, and is one that we can see physically. In fact, mathematically, the coherent states are actually eigenstates of the annihilation operator. This is relatively straightforward to show now, though we will leave that as an exercise rather than going through it explicitly here. Remember, of course, that the annihilation operator is not a Hermitian operator and does not represent an observable physical quantity. But this mathematical statement that the coherent states are the eigenstates of the annihilation operator is still quite a valid one. We had introduced the coherent state before when we were discussing the harmonic oscillator. And there we saw by specific example illustrations that it oscillated at the frequency of the oscillator. The same is true here, where now that frequency is a frequency associated with our electromagnetic mode. In this coherent state, the electric and magnetic fields do not have precise values, just as the position and momentum did not have precise values before in the mechanical harmonic oscillator. As the average number of photons in the mode increases, the relative variation in the values of electric and magnetic field decreases, and the behavior resembles a classical pair of oscillating electric and magnetic fields ever more closely. We can see this by looking again at these oscillations for different average numbers of photons in the mode. So let's look then at some oscillations in coherent states. Formally, we're looking at oscillations with the following functions that we've written before. We will also now write them explicitly in terms of this coordinate, xi lambda, and time. And remember that xi lambda is really the amplitude of the magnetic field mode. And as before, of course, our coefficients are just given by this distribution. That's the square root of the Poissonian distribution. And as I said, xi lambda is the magnetic field amplitude. So here's the oscillation when we have n bar equal to 1. That is, the average number of photons in this mode is 1. Now, incidentally, in the coherent state, n bar does not have to be an integer. What we're seeing here is that the magnetic field amplitude is indeed moving from large values positive to large values negative and back again, and it's oscillating backwards and forwards at some frequency here. But it's not a definite value. This is a probability distribution of what we would measure at each specific time here. So indeed, there's an oscillation going on, but it's an oscillation of a probability distribution back and forwards. As we increase the average number of photons per mode, this probability distribution just gets narrower. So if we look at 3 photons per mode, we have a relatively speaking narrower probability distribution. Actually, the absolute width is increasing, but relatively the width is getting narrower. The amplitude is actually larger now of this oscillation from side to side. And if we increase to 10 photons per mode on average, then we get a larger amplitude of oscillation. The width in absolute terms has actually become slightly larger of this probability distribution, but relatively speaking, it's become smaller. And if we increase to an average of 100 photons per mode, then we get an even larger oscillation here in the magnetic field amplitude of the mode. Relatively speaking, the width of this distribution has become progressively smaller compared to the amplitude as we've increased the average number of photons per mode. So this is corresponding more and more closely to our classical idea of an oscillating magnetic field in this mode.